Now, GigaChat, something that we have heard many times here on this hall, and this is a tool that helps a lot of people. Now, smart search engine, idea generator, recommendation generator, and the developers of GigaChat, what do they write to each other when they develop their product? The technical director of the GigaChat service and the team lead of GigaChat created the GigaChat Dev Notes. That's the interactive session that we're going to have. And please welcome Fedor Minkin and Valery Ternovsky, who is going to have a presentation afterwards. Now, GigaChat Dev Notes. Hi, everyone.
Меня зовут Федор.
My name is Fedor. I am a technical director of GigaChat service. I'm going to talk about how we developed it, about its features, and the notes that we took. What is GigaChat? GigaChat is a multimodal AI system that you can use to communicate with. You can resolve your tasks using that, and it can work with text really greatly. If you need to have a summary of something, to write some argument, to do something with a text, or like to rewrite a text in different style, GigaChat is going to be a fantastic tool. It can code in different programming languages, it can remove the bugs from the code, and it can actually help you in different tasks. We also use GigaChat to communicate with the users. We have a GigaChat service where you can talk with the chat, generate some texts, resolve some of your tasks. In terms of multimodality, it can draw pictures, and my colleagues said how it goes about it, and we use the service to make great pictures. It also can use a search context to make sure that your search results are as accurate as possible. Now, what I wanted to talk about today is the update of GigaChat. GigaChat became smarter. It has fantastic models. One model for 7 billion parameters. It's already working. It's live. Can you connect it through API? 29 billion parameter model is going to be another next-gen model of GigaChat that will make it much, much smarter.
Как раз расскажу, как мы его разрабатывали.
I'm going to tell you how we developed it, this new generation of GigaChat. 3 main stages. I'm going to talk about the first one, and the second one is going to be covered by my colleague. Pre-training, that's the first stage. During this stage, we gather the documents around the world. That's a digital footprint of humanity, basically. We train the GigaChat to predict the following tokens in these documents. We make it learn all these documents. On this stage, GigaChat gets its intelligence, its capability to resolve intellectual problems, to provide factual information. It learns the languages, and basically, this is the stage where we develop its intellect, intelligence. And as we get this GigaChat with all the humanity footprint in it, we need to understand what people want from it. Not everything from this digital footprint is right, and we have to filter it. It's called alignment. The first stage of this alignment is fine-tuning. Like, if someone wants a summary, this is how you do it. And then reinforcement learning. Reinforcement learning is more about the details. Like, yeah, we follow an instruction, and we need to make sure that you don't miss any steps. Now, that's the first step. For pre-training, there's a good recipe for ML. You get a lot of data, you select the architecture, you fine-tune the model, and you train it. We failed to do that, so we had to go through some other stages. The first one is that to train GigaChat, you need a lot of GPUs. And there are many engineering problems that appear when you use, even when you use supercomputers. And we have became an expert in CUDA, improvers in PyTorch. We looked at garbage collectors in video on the video cards, on the GPUs, and we have gone through all of these barriers, and we were able to get a great model, language model. But the first step that is required are data. You won't be able to achieve anything without data. And there's quite a lot of challenges here. First of all, there's not a lot of open source Russian data sets. If you compare it with data sets of ChatGPT and others, well, we are lagging behind, at least in open source. And so we have to reassemble the internet. We need to get all of these saved pages from the entire internet to clean it up and to get the relevant information. We need to take a lot of books, but they're all in déjà vu on PDF formats. Those who were using the electronic books know about these formats. Now, filtering out the internet content in the books is a very costly operation. And there's also a multi-modal feature, like formulas and images, that you need to transform to the text, or then format that to make sure that GigaChat understands that and it can resolve physics problems. Now, I'd like to also say, how did we filter the internet? There were 6 stages for filtering out the internet content in our devices. First of all, we used 5 years of internet content from 2018 to 2023. We got only 5 years. But because to filter them out, we need 6,000 cores and 60 days of continuous work. Then we understood what languages we need, Russian obviously, and of course English, because there's a lot of information in English.
So we had to clean all these volumes. We created a 2-stage classification process and internet page cleaning process. The result was a certain amount of pages with duplications. So we had to deduplicate them to get only unique information. And then there was one more step to get rid of one more piece of waste, the repeat elements such as ads. How were we doing this cleaning, the 2-stage pipeline in internet page cleaning? The first stage was a simple classifier. We have this page transformed into text. Did the conversion happen? Was the conversion good or not? We did the classifier based on a smaller model, and we got a great document where everything was perfect. Then we took a document in yellow with some low quality inclusions and a completely inappropriate document. We cleaned the parsing mistakes, and then we decided to correct the yellow documents, which had both good and bad information, because we did not want to just throw away half of internet. The task was pretty similar. There is a paragraph. Can we remove this paragraph without adversely impacting the text as a whole? Because in the text we constantly had advertisement blocks, errors, and if we could just remove those, that page without the removed paragraph would be perfectly suitable. The metrics on the right also, we were able to clean it without having dirty data turn up in our training data set, so the precision is very high. and we saved the 50% of pages that we could save theoretically. What we ended up with was, out of the billions and trillions of pages, let's take the nice number of 100,000. We managed to clean 59,000 of them. On the slide, you can see how we did that and the loss ratio at each stage of the pipeline.
Чистый интернет.
Thanks to this, we got a cleaned up internet. Our dataset looks roughly like this. 69% is multi-language internet, 17% books, 8% code, and 6% articles. The rest is negligible. This dataset amounts to almost 2 trillions of tokens, terabytes of data. And on the right-hand side, we see how the cleaning was reducing our dataset. If we take the main languages for 100% after the cleanup, we ended up with 59%. Out of the 59%, if we take only unique texts without copywriting, without similar pages, without full copies, out of the 59, we end up with around 20%. So we have reduced the internet almost by 5 times to fit it into GigaChat. We used that data set to train our 2 models with 7 billion parameters and 29 billion parameters. After we got the data set, we had to finally use it for training. And now about the training. On the right, you see the loss. Even though it's difficult to compare models by a loss, we see that the 29 billion parameter model has a lower loss value and it can digest more information. And about the similar features with the 2 models. The optimizer is Adam. The other optimizers did not demonstrate good results, and there is an option that with the optimizer is responsible for the aggressiveness of training. Our epsilon is 1e to the power of -8, which is not really comparable with the epsilon 1e to the power of -5. Of course, we wanted to be more aggressive in our training, but if we took the magical epsilon, the problem was that the training just stops at some point. The network just stops training. We decided to dig deeper into this problem, and we found out that the problem was the tokenizer. It transfers text into a sequence of sub-words or letters used in training. A tokenizer with a large number of tokens had a very negative impact on the training, and the network just blows up. So we selected the comfortable number of tokens, 42,000 tokens. The tokenizer was largely efficient for the Russian language, more efficient than the tokenizer of ChatGPT-3, 4 letters per token, on average. Another distinguishing feature, each digit is a separate token. This improves the mathematical side of the model. We used rotational embeddings, which were used in order to expand the context after the training and to be able to effectively build models with larger context and a better understanding of longer texts. The rest of my presentation, to understand the rest of my presentation, I think I should first talk a bit about MMLU. This is similar to an exam. You have questions with multiple choice, 4 options. You see this example in English. A question, 4 options. One of the 4 options is correct. We use the same method, same as other companies in the world. We use it to evaluate the capabilities of the neural network. It is not exactly correct to compare models by loss or failure rate. It could yield bad results, so we use this benchmark, MMLU, for comparison. Out of the obvious things, the maximum is 100%, and the model that guesses randomly yields 25%, so the dataset is balanced. Our training took 2 trillion tokens, and the models at different periods of time, they start understanding this benchmark and demonstrating real knowledge. The 7B model started demonstrating after 6 billion tokens, and then the other model, we show it 250 billion tokens, and it already starts growing. 1,000 video cards were used for both models, 7B 10 days, 20B, 27B 40 days. So this is a much more expensive computational network. We try to use the maximum capacity of the supercomputers of the video cards. We want to train it faster. The bigger the model, the more time it takes, and we want to build even bigger models, which means the training will take years. So we decided to add some new techniques to speed up the training. The first thing we wanted to do is to remove the checkpointing of activation, which is where we do not have enough storage space because the models are the networks are so big, and so the caching takes place within the duration of the training. We were able to optimize the RAM on the video card. We optimized it through adding glued together layers, the fused layers, fused rotary embeddings, and other fuses. And we sped it up more by 50%. We embedded the flow attention to the commodity. We improved the collateral of documents. This is how documents are batched together. We minimized excessive redundant communications because we had so many training nodes. Communication was a problem. On one video card with is communicating with the 999 other processors, this slows down the communication. So what are these excessive communications? In more detail, the forward through the network, the backward, we calculate the gradient, and then communication where gradient is communicated to all the nodes in the cluster. At that point, nothing is calculated. We optimize this moment, and now only 10% of the cluster is there waiting for communication. This is a super cool result. We started with 40%. 68% is calculated. This is calculation. We continue calculating the new batch and continue communicating. And then there is real communication, real calculation without communication slowing it down. Synchronous batch collector. A big problem that we were able to solve. With a certain node, this error arises where there is not enough memory left. The user does not see it, but the system knows it, and it tries to compress everything on the video card into a smaller topology. This is akin to defragmentation of an RAM on a computer. And at that point, everything just freezes. And if we multiply that problem by the number of nodes, we will see that at each point in time, something gets frozen, and this obviously slows down the training. On the diagram, you see that this slows down by 5 times in extreme scenarios. If we clean up the waste arbitrarily, whenever the video card wants it, the training slows down by 5 times. We also see the diagram for increasing attempts to reallocate the memory because it is occupied. Our solution was to clean up the memory across all the nodes in a certain iteration. So at a certain point in time, we clean it up, we slow down, but we remove this strange effect. This provided a very big boost to the speed of training. As a result of all these optimization methods, with this 7B model, we reduced the training time to 5.5 days. The attentive people in the audience will remember that I showed 10 days, but now we do it in an even shorter time. And now about the metrics. I just wanted to briefly describe the metrics. The MMLU metric that I described earlier, 13 billion parameters with the older GigaChat and the new generation 7B and 29B. What's interesting is that we are ahead of the foreign neural networks with the English-speaking benchmark, English language benchmark. MMLU is 7. Same goes for 29B. As with the 7B model, but we have ideas about how to improve the MMLU for the 29B model. We are ahead of our counterparts, and we are going to continue improving the pre-training metrics. Another important metric is side-by-side. This is where the model is not being asked artificial questions with 4 options, but instead we are trying to communicate for it to communicate with the user in order to assess its skills. We have 10 different categories of communication, and on the left-hand side are the 7B metrics and the 29B metrics on the to the right from you. Basically, this is on par with ChatGPT 3. With some topics like brainstorm, it is a bit worse. With the text summarization, we are better. So the average is 50-50. 7B is also very good for the model of its size. In addition to communication with the user, we have another metric. Out of these other metrics that we monitor is this, a law exam. If you pass that exam, you get accredited as a lawyer. And so we try to get our network to pass that exam. The old model, on the right, you see that on the diagram, it completely fails. 25% of correct answers. 7B, 63.5%, and 29B, it achieves the threshold and gets 80% of correct answers.
Thank you. Apart from communicating with users and apart from going through exams, GigaChat can be used for other things. GigaChain, that's a link chain, LangChain, with the Russian prompts, with the prompts translated into Russian, and you can resolve some business problems with it. You can not only communicate with the users, but you can create your own assistant, or you can bring AI to your product. To wrap up, I would like to tell you that together with Physical and Mathematical University, we are organizers in a hackathon based on Kandinsky and GigaChat. You will need to create an assistant, a solution. So I encourage you to participate and use our enhance. Valery Ternovsky will now talk about how we make GigaChat follow instructions and resolve problems. Well, hi everyone. I'm going to try to be very quick. Talk about the alignment stage that Fedor mentioned. And I'd like to give you some overview and how we worked on our model. Now, what we started with, we didn't have our pre-trains like Fedor talked about. We had 13B model. That was even worse than the current 7B, but we had to start with something. What did we start with? Now, back then, there was very few open data in Russian language. So how did we try to resolve this problem? We got some resources, and potentially they could be used to get some quality, well, at least some data of some quality to be suitable to train a model. And when we looked at this website in the manual mode, we got some structured manuals, and It looked like an instruction because we kind of compiled it in the instruction mode, and then we use FTP pipeline version 0.01, and we have side-by-side metrics here. We were, competing with ChatGPT, but I mean, obviously the result was not that great. 10 by 90, 10 out of 90. But what did we do next? We then diluted our bad data with good data. At the same time, we launched a process to generate data by our fantastic experts and our editorial staff and other people, other experts, and we tried to fill in this instructive data set by diluting the synthetics with by diluting bad data with good data. 15 out of 85, still not great. Our next milestone in SFT pipeline is the validation of data. It's the same as in other projects, basically. The validation of data is almost always gives you more quality. The same with us, but the old pre-train was our kind of glass roof for us. 30 out of 70 was the best result. But when we made the alignment of all of our connections, we got 35 by 65. This is something that was a milestone that we couldn't really pass. But then we have 7B pre-train that Fedor talked about. 29B was 50-50. We have showed already. Now we were making our SFT pipeline we're putting it into industry, making sure it can work in industry applications. We had a separate stream for research, and when we had a good pre-train on this stage, it was very important for us to remain afloat in the area of the research initiatives, because there's quite a lot of articles that are being published regularly, and we have quite a lot of ideas as well. And we decided to divide our production activities, because we have a research and we have the data replenishing activities. Now, this research stream helps us to test drive some of the measures, some of the new solutions. Now, just a few words about RLHF. I don't have time to talk about that in detail. RLHF is something that we know about. Now, RLHT is something that we have already used. RLHT was a model that could be used for specific use cases or security, for example. Now, we have a special stand. We have a special booth on the ground floor of this conference center. I'd like to tell you that rejection sampling worked great. It increased the efficiency by 7%. It's using LM for data generation and the reuse of this data. Like, we send it for further training. This scheme has been used in the industry to resolve various tasks. Well, basically, that was it for me, for my small presentation. Use GigaChat. I encourage you to do that. Thank you for your attention. Well, thank you so much for that exciting presentation. Thank you for Fedor and Valery.